All right, so we'll now talk about aggregate and magic square and optimization problems today. And this will conclude the answer set programming portion of this course. Okay. So sometimes when we have aggregate, some of the program can be written very succinctly. Okay. So what is an aggregate? Aggregate in general is a function that maps some sets to some numbers. Okay. So you can think about counting as an aggregate. So you want to count how many elements are there. You want to also sum up summation over some numbers. And you want to find the minimum value or the maximum value. So the common property of these functions is applied to sets and return some number. Okay. So we'll first talk about the counting, and let me ask you, maybe based on what you know now, okay, what this will be about. So we actually did counting before using the lower bound and upper bound. Okay, but here this is actually the counting the y values, or counting how many different y's are possible given that h, x, y is true. Okay, so this will return a number. Can anyone give me what is intuitive reading of this expression in English? So we are counting how many different y's are there such that edge of xy is true. So in simple English, it means that how many outgoing edges are there from the vertex x. Right? We did something similar in the Hamiltonian cycle, although we didn't use the count aggregate. So here you can say given particular x, we are counting how many y's are possible. Okay, so how many different vertices are connected from vertex x. Okay, so we can write this kind of rule. So we want to know, given a graph. So imagine that you have given a graph that consists of vertex and edges. What we are doing in this rule is given the vertex x, we want to count how many outgoing edges are from the vertex x. And that number is represented by n. Okay, in graph theory, this is called out degree of vertex x. Okay, so if you see the vertex x like this, and if it is connected to, let's say, 1, 2, 3, okay, the value of this counting is 3. Because it has 3 outgoing edges. Okay, so we're actually counting how many vertices are connected from the vertex x. Then there are 3 vertices, and this number of vertices are same as the number of outgoing edges. Okay, and we can also talk about the branching factor of the vertex. So branching factor here means exactly the given the vertex. Okay, actually, we can say what is a branching vertex. So here, if you have more than one outgoing edge, then we call this vertex as x as a branching vertex. Okay? So you can write this inequality. Okay? The number of y that is connected is greater than or equal to 1, means that at least there are 2 different outgoing edges. So here is a different thing. In this case, counting is count the pairs of x and y such that edge xy is true. Okay? So what is it actually counting? So before I said it's similar, but the first one has only y as the counting thing. So we are only counting how many y's are possible. But this time we are counting how many xy pairs are possible such that edge of xy is true. So what is actually being counted here? Very simple, right? We are counting the number of edges. right? So we are counting, given the graph, this rule is saying that how many edges are there? Because we are counting the pairs of the vertices, and each pair of vertices is exactly the edge. So we are counting how many edges are there in the graph. Okay? What about this? This time we have 3 variables on the left of column. So x, y, z, such that edge xy and edge yz is true. So what is being counted here? Any idea? It's counting the passes of length 2. So if you have 2 edges, right? So basically, for this to be true, there should be 2 edges, edge xy and edge yz, that should be connected. Okay? So it's counting the number of length 2 paths. Okay? So one syntax thing that you have to worry about is when this aggregate appears, you can either write equality or inequality with respect to some number. You cannot compare between the 2 aggregate. So count of this one is bigger than count of this one. You cannot do that directly. If you want to do that, you can introduce the variables saying that this is equal to n, this is equal to n1, and n is greater than n1. So you can write in the syntax, but you cannot directly write inequality between the 2 aggregate. That's just the syntax limitation of Klingo, but it's not actually very inherent difficulty. So you can easily introduce the variables to represent the values. Okay? Any question about this part? No? Okay, Saraj?
Yeah, so does this part, will it instantiate on itself too, or is it already?
So we are given a graph. So there is a separate file that lists all the facts about the edges and vertices. Okay, then we know what is true, what vertex are true, what edges are true. So then we can count on this. So this is not a standalone rule. This could be added into one of the graph problems that we did, and then it will show all the properties about the graph, like arc degree and number of lengths, 2 paths, and so on. Yes?
Would that count 2 edges? Could it count the same edges itself?
Yes, true. True. Yeah, that's true. So here, x, y, and y, z is not necessarily distinct things. So maybe more correct way to say it is passes of length up to 2. Okay, well, good point. Yes, xy, yz can be actually the xy can be same as yz. So in that case, it's actually counting the same edge twice. Any other question? All right. So you can do a lot of interesting counting about the graph using these. Now, as we just saw, when you have the left side of the column, there may be more complex terms there. So here is an example. Okay, so let's pause. What we are counting is how many different x times y possible that satisfies the conditions on the right-hand side. Okay, that's what this is about. Can anyone see in intuitive English, what does this counting? So we are counting x times y such that the right-hand side is true. What is it, the thing that we are actually counting? How many products? How many composite numbers are possible? Yes, yes, right. So it's actually not just the product, but the values of product or the composite number itself. How many composite numbers are possible? So let's see why. So here we have x times y. We are counting it, but x goes from 2 to n, y goes to 2 to n, but x times y is less than or equal to n. So we want to count up to n. How many composite numbers are there? Composite numbers are the numbers that are multiplied by 2 numbers okay, that is not 1, right? So product may contain 1 times x, but here we are not doing that. So these are composite numbers. So composite numbers are the things that you can represent. It's actually, composite numbers are the numbers that are not prime numbers, okay? So it has, the prime numbers are the ones that have 1 and itself as the only factors. But here, these numbers are not, okay? So let me ask you then, so what is the value when n equals 5 here? What is the value when n equals 5? Nathan? 1. And which one is that? 4. 4 is the only composite number between 2 and 5. Right? Okay, good. Are we together? We are talking about the composite number, right? So when n equals 5, what are the possible pairs that you multiply so to get the value less than 5? Okay, so I cannot make 1. Okay, x times y cannot be 1 because x and y start from 2, right? X times y cannot be 2 because, okay, the x and y ranges over 2 to 5, right? X times y cannot be 3 because I cannot have 1 times 3 here. 1 is not part of this range, right? And 4 is only possible because 2 times 2 is 4. We are done. 5? No, 5 is not possible because to do the 5, you need 1 times 5, but we don't have 1 in the range. Okay? So only 4 is the composite number less than or equal to 5. Okay? And so because of that, we count only 1. Okay, so the next question for you. Let's do the Socrative. When n equals 10, what should be the value? Now the question is, when n equals 10, what is the value of this count aggregate? I was asking about the value. Count, what does this count function returns? Count function returns a number. Okay? Okay, so let me open this. Okay, so there are many diverse answers. 5, 4, 8, 10, 2, 5, I don't know. 4, 6, 8, 9. I was asking that to give a number of count, the value of counting, not the instances. And okay, so the answer is 5. Okay, why? Because we are asking about the composite numbers between 1 and 10. So what are the composite numbers? 4, 6, 8, 9, 10. Those are the composite numbers. 4 is 2 times 2, 6 is 2 times 3, and you can find it, all right? So there are actually 5 composite numbers in the range, so the answer should be 5. All right. Now we actually look at this one, which is the lower bound and upper bound. So what was this rule saying? We are trying to give find the subset of the vertices that have n elements in it, right? So n element subset of the vertices. We can also write equals n when the lower bound and upper bound are the same. But now we also have third choice to write this rule. So the first one is in is a subset of the vertices. But then we say in the next line to give a constraint. If the number of elements in the in predicate is not n, then this violates the constraint. In other words, the element the number of elements that belongs to the in predicate should be exactly n. Okay, so these two rules are actually same as the rules above. Okay, so here we just say that just choose any subset of the vertices, and then we say that this subset should contain exactly n elements. Okay, so you can write that way. Here is an exercise for you. Okay, so this one is a bit different. Okay, so here we are trying to find the P is a subset of Q, but contains at least 5 elements and at most 7 elements. Okay, how do we write this thing using the count aggregate? So, following this spirit, what we can do. So the first line is actually same as before. We are trying to count any subset. So P of X is a choice. So we can either choose the elements that belongs to Q in P or not. Okay? Because of that, the set denoted by P is a subset of the set denoted by Q. But then we have to control the cardinality. So this P should contain at least 5 elements and at most 7 elements. How can we enforce this idea? Anyone wants to try? Yeah. You have credit already, right? Okay, so let me ask you who doesn't have the credit yet. You can? Okay, why don't you write the solution here? I think you tried multiple times. I'm surprised that you still don't have the credit. So I wrote first line for you. Just write the other rules as needed. Time. Pardon me? So you're not sure about your answer? The answer is actually wrong because syntactically it's even not true. I told you that you can have count value equals some number. So comparison is here. You cannot write 5 and 7 over there. Okay, so that's not possible. Anyone else? Okay. So while he's writing the solution, let me actually move on to the next work. Okay. So so here is yet another exercise problem. Okay. So we have PA1, PB1, PB2, PC3. So we are going to count it, and for the Q, note here that the difference is what we are actually counting. Okay. So let's actually do this together. For the Q value, we are counting how many pairs of AX is there. So what do you think will be the value of Q of n? This is same as before, right? So we are counting how many distinct pairs of AX is possible, such that P of AX is true. What should be the value of Q of n? So let's see. We are counting how many pairs of AX satisfies this equation. I can count 1. A comma 1 is one possibility. B comma 1 is another possibility. B comma 2 is another possibility. C comma 2 is another possibility. We are counting how many AX. This is AX. This is AX. This is AX. This is AX. These are all the different values of AX. So what should be the Q of n? Q of 4. So there are 4 distinct pairs of AX. Okay, so the answer here is Q of 4. But what about R of n? So in the case of R of n, we are counting the distinct A as long as it has some X pair. Okay, so we are counting how many A's are there such that it has some X such that P of AX is true. So how many A's are there? 3. Why? We are counting only A, B, C. Because A has some X, which is 1. B has some X. Actually, there are 2, but I don't care. Because I don't count X, I can count only B. So that's actually a 1B there. And same for C. So in this case, R of 3 is true. And now the same reason. What is the S of n? S of n is counting how many X is possible. So 1 and 2 are possible. So that's the value. Okay. So in order to find out this, just try to enumerate what are the values of A and X. Okay. So in the first Q case, we are counting all the A and X pair. But in the second, the next one in R, we are counting only how many first elements are there. Okay, which is 3. So because A, B, C, there are 3 distinct elements. And for the S, we are counting 2 because 1 and 2 are there. Okay? All right. So then, now let's go back. Can you come and explain? Aha. By the way, why don't you write your name? Are we satisfied? One objection. Okay, what is? Aha. So what is wrong with this one? If you do this, yeah. And there's no such thing possible, right? So basically, adding this is just to add bottom there, which is always false. Do you see?
Yeah, so they have to be 2 separate statements?
I don't know. Let's try. Will that be okay if you just put just period? No. Okay, can you just write in 2 lines so that people can easily see? Okay. So in the first line, it is saying that the number of x that belongs to px qx, if it is less than 5, then it violates the constraint, right? And in the next line, if it is greater than 7, then it also violates the constraint. So in order to not to violate this constraint, the count should be between 5 and 7 inclusive, right? Any doubt? Looks good to me. Maybe you can count both of them too. Kian and Ziad. Both of you already have credit, right? Okay, good. All right, so so that was the answer. Good. And we did this. Now, there's another one, which is summation. And in the case of summation, the rule is slightly different. The counting works for any set, but the summation works for only the case where we are counting the numbers. We are summation over the numbers, right? So maybe it's better to see the example. Okay. So in this program, we have 2 atoms, P1, 10 and P2, 20. Okay, and we want to sum over the values. Okay. Now, what are the things that we sum over? XY pair, such that XY belongs to PXY. So, how many different possibilities? So here we have, actually, let's say 1, 10. This is XY pair, possible. Another is 2, 20, because these belongs to P, right? So this is my XY, XY. If I count XY pair, then there are 2. But this time we are sum over the elements. But which one do we sum over? Okay, there are 4 numbers here. Okay, are we sum over the first? Are we sum over the second? Or are we doing the sum over these? So what Klingo follows is for each element pairs, we are counting only we are summing over only the first element. So if we write this way, we have created 2 XY pairs, right? But when we apply the sum, we sum over the x values. Okay? That's why the convention. So it's called the weight. And when sum calculates, then it is counting, it is summing over this weight. Okay? So what is Q of S in this case? We are doing the summation over the first elements. 1 plus 2 is 3. So here Q of S, the value of Q of S will be Q of 3, because it's 1 plus 2 equals 3. But if I do this R of S, this time we are also considering same P, but we reverse this order. Okay, so what we are counting is Y values. Okay, we are summing over the Y values. So PXY is still the same. Okay, we have 110 and 220, but we are counting Y's. And the Y's are 10 and 20. So when we add up, R of S here will be R of 30. Okay, so this is what you can verify using Klingo. Okay, so the next one. Actually, let's do this with Socrative. So I'm asking you to find the stable model of this program. Okay. So the difference between the first and second is what you have on the left-hand side. Okay, left-hand side of the column.
Is this using the same key?
No, it's a different one. It's just a standalone program. Okay, so okay, so let's do this together. Q of S, let's do this first. In Q of S, we are counting how many n squares are possible when, what is the sum of all n square when n goes from -2 to 2, right? So what are the values possible? When n equals -2, -2 times -2 is 4. When n equals -1, -1 times -1 is 1. When n equals 0, 0 times 0 is 0. When n equals 1, 1 times 1 is 1. But 1 is already there. Look at this. This is a set, so we don't need to recount this. When n equals 2, then 2 times 2 is 4, which is already there. So we are now counting this thing. We are looking at this set, and we have the sum over all these elements. So that's 5. So Q of S will return Q of 5. What about P of S? In P of S, we actually have the tuple. So the first one is 4 when n is -2. And 1 when n is -1. Look at this. I have n times n, comma n. So this is what I write, n times n and n. 0 times 0, 1 times 1, comma 1, and 4, comma 2. Now note here that unlike the previous case, we have the second element distinguishes, right? So even if we have 4, -2, that's different from 4, comma +2. Okay, so and these are the sets. We are not counting the duplicate elements. But this time we have 5 elements in it, and we are adding the first tuple, first element. So 4 plus 1 plus 0 plus 1 plus 4. So that gives P of 10. Okay? So there's subtlety in what you put on the left-hand side of column. Okay, makes a difference. Okay? So So this technique is actually used when you have to count this n times n in a different way. So we want to count multiple times when n is different. Okay? So how do we do that? We write the second element to distinguish that 4, negative 2 is different from 4, 2, so that when we sum over, we are counting for twice. Okay, so that's what we have here. Okay, so this is an exercise problem. You can check it using Klingo, but try to do this by yourself and see whether Klingo returns the answer that you expected. All right, now the magic square. So what is the magic square? Again, this is like a grid, the grid puzzle where you have n by n grid. And we are talking about the basic version of magic square problem, where you have numbers from 1 to n squared that you can fill in. And it's similar to number snake as we did, but the constraint here is now all the sum of the rows and sum of the column and sum of the two diagonals are all the same numbers. This is called the magic constants. Okay? And in fact, it's not too difficult to find out what this magic constant will be. It's either 1 plus 2 plus up to n squared divided by n, because that's the number that you fill in all positions, right? And if you have 3 columns, you have to divide evenly by, if you have n columns or n rows, you have to divide evenly. So all the sum of the numbers that you fill in the grid divided by n is the number that you have to sum up in each column or each row or diagonal. Okay? So this is one solution. So as you see, 2, 9, 4, when you add up, that's 15. 7 plus 5 plus 3 is also 15. 6 plus 1 plus 8 is 15. You can do the row wise, that's also 15. You can also do the diagonal. This 2 diagonal gives 15. Okay? Are we together? All right. So now it's your turn. So this is 4 by 4 grid. Okay, and you have to place 1 through 16. First, what is the magic constant here? Okay. So 4 plus 4 cubed divided by 2. Okay. So 4 cube is 64, 68 divided by 2, 34. Meaning that when you add all the numbers here in each column, each row, they should be 34. Okay, let me give you 1 minute to think about. Can you fill this grid? If you have a solution, raise your hand so we can write. let me just continue, and if you have found some solution, you can tell us later. So our goal is to solve this problem using Klingo. Okay. Now the first part of the program is exactly the same as what we did in the number snake, because in number snake we had to place 1 through n squared into an n by n grid. So we are doing the same thing here. Okay, if you forgot about this, just go back to the previous lecture. Okay, now what is the magic number? Magic constant here is n cube plus n divided by 2. Okay, that is a fixed number. So we just write the constant declaration. Now this is the part that is unique to this magic square problem. So we have to say that every row sums up to the magic constant, right? So in n, when n equals 4, all the numbers in the same row should sum up to 34. Okay, how do we represent this? Now using the sum aggregate is actually easy. Okay, so we are counting what are the values of x in the same row. So row here is the global variable. So each row, so let's say row number 1, we are summing over all the numbers in the row. Okay, and if that is not the same as the magic number, magic constant there, then this violates the constraint. Done. Okay, the next is also easy. Every column has to sum up to the magic constant. Basically now we are counting the same column, right? So given the column, okay, given the column, sum over all the elements x. And if that sum is not the magic constant, that is also violate the constraint. Easy to do. What about the diagonal? Well, there are 2 diagonals here. One is left to right, which is represented by r, r. 1, 1, 1, 2, 1, 1, 2, 2, 3, 3, 4, 4. So add all these numbers in that position, and if it's not a magic constant, then it violates the constraint. Now what about the things on the other diagonal? So the other diagonal is actually represented in this way. So if we have 1, then 1, 4, and 2, 3, 3, 2, 4, 1 is represented by this equation. And if you sum over all the x, okay, if that's not the magic constants, that violate the constraint. So that's it. Okay? So the first 2 rules over there are exactly the same as number snake. We just put the number from 1 to n square into n by n grid. But then for this magic square problem, we are summing over all the rows, summing over all the columns, and summing over 2 diagonals. And that sum should be always equal to the magic constant. If it's not, then it violates the constraint. Okay? And that's it. Okay, anyone found the solution? Yes. Can you write your solution? Okay. Any question about this program? You want me to explain again? Okay. All right. So let's see. We have to sum up to 34, is it? Right? Doesn't. Okay. 429, 1. You have 2 4s here. Am I right? So it should be 1 through 16. Okay. Anyone else? Do you have right answer? Okay. All right.